it's easy to calculate slope information for this graph. The slope of the first segment, well, we have a change in velocity from 13 to 11 of -2 centimeters per second over a 3-second interval from here to here. So that is -2 centimeters per second divided by 3 seconds, -0.66 centimeters per second, or centimeters per second squared if we want to represent it strictly as an algebraic quantity without worrying about what it means. Between clock time 3 and 6 seconds, our velocity increases from 11 to 17 centimeters per second. That's an increase of 2 centimeters per second. That's an increase of 6 centimeters per second over a 3-second interval, which gives us an average rate of change, or an average slope, rise over run, of 6 centimeters per second divided by 3 seconds plus 2 centimeters per second. And a similar calculation for the 10 centimeter per second rise between here and here over the 3-second run gives us a 3.33 or 3 1/3 centimeter per second squared acceleration. Again, representing the change in this coordinate, that's the rise, divided by the change in this coordinate, which is the run. Sticky finger. Okay. There's another quantity involved with the slope. We note that at clock time 3 the slope goes from -0.66 to +2. That is clearly a change of what? 2.66 centimeters per second. That change was based on slopes that were calculated on uniform intervals of 3 seconds. So we say that per second of this time interval over which we calculated the slopes, whose changes we're calculating here, over a 3-second interval, the slope changes by 2.66 centimeters per second. Well, we take the slope change and divide it by our delta t, which is 3 seconds, and we get what's called the rate of slope change. The slope change of 2.66 centimeters per second squared over a 3-second time interval gives us an average rate of 0.87 centimeters per second squared per second. Now that's a little bit of a mysterious quantity. It's going to be difficult for you to relate to it right now, but that's what it is. And here we have a change from 2 to 3.33. That's a change of 1 1/3 centimeters per second squared over a 3-second interval, or based on a 3-second interval, gives us a 0.44 centimeter per second squared per second rate of slope change. The slope represents what we call the derivative of this function. So that when we take the slope change, we're taking the slope of the derivative, or the change of the derivative, and the rate of slope change is the rate at which the derivative changes, which in a sense is a derivative of a derivative. This is an interesting and important idea.